magnetic types. Another one is capacitor types, voltage transformer. So the basic operations of these two different types of voltage transformer will be introduced to you, as well as its purpose in the electrical power system. Then the second topics here will be about the current transformer. In short, is CT. We are also having two types of current transformer. So based on how does the primary circuit is being configured, we have wound types and the bar primary types current transformer. So we'll see what is the difference in terms of its constructions, working principles and all. So it's very important for you to take note that for voltage transformers or current transformers, that is what we call it as the magnetization curve, in which we can actually extract the useful information like what is the knee point voltage here, in order to ensure this instrumental transformers here can able to work in proper manner, which means that it will give you the right measurements. And at the same time, during the time, if you want to select the right current transformer to be used, there are different factors to be considered, like what is the accuracy limits or what is the maximum burden can be connected at the secondary side and all. Yes, this topic will be covered as well. And towards the end of chapter 3, the last topic will be covering what is the possible problem faced whenever we are using a current transfer in the networks for current measurements. So with such a case, we can pay attention to this to avoid any wrong information being measured. So these are the topics we have in chapter 3. All right, so now the lesson learning outcome for chapter 3, we have 3. All right, so now the first one will be to understand different types of instrumental transformers we have. Referring here would be the current transformers and the voltage transformers. What would be its working operations, as well as how it's being built in terms of constructions by looking into its equivalent circuit, right? That is the first lesson learning outcome. The next one here is time to analyze. So again, there will be some calculations involved, but this time we'll analyze how does the instrumental transformers here become saturated. So which means that you need to find what is the knee point voltage value, what would be the maximum burdens or load can be connected to this instrumental transformers here, so that we can prevent it from out of proper operations. That's the second outcome you can get. And after this, right, so after learning the principles and the constructions of both current transformers and voltage transformer, it's time to look what are the difference between them. So you are able to distinguish what are the difference between the current transformer as well as voltage transformer, and what would be the precautions you have to consider whenever we are using them in the electrical power system. All right, so now let's move on to the next slide here. So I have a figures as always. You see every time I start the new chapters, that's the overview diagram of the electrical power systems. So I hope that you can get a better visualizations whenever we're going through these chapters right now. So now we know that this is an induction motor that we want to protect. This is the components to be protect. And these motors will be supplied with the three-phase voltage source, or I should say three-phase power source. So right now in chapter 2, the two important components that we are putting focus on would be the CT and VT, and this is where they're located. So CT are the current transformers, and here VT is a voltage transformer. So the purpose of this CT and VT is like act like a sensor through the protective relay. So it will send the informations like the measured currents, the measured voltage as an input, so that this relay able to recognize if there's a fault occurs within the protected equipments here. So in physical form, this is how it looks like in the substations. So this is current transformer and this is the voltage transformer, like a lifetime design. Okay, so take note that for both current transformers and voltage transformer, we're actually using three, right? Three current transformer, three voltage transformer. Then we are measuring a three-phase current and three-phase voltage. So if you notice in proper manner, right, these three current transformers that actually connect in Y connections. So one of the terminal will connect to each phase, like this is for A phase, this is for B phase, and this is for C phase. And other terminals here will connect to a common neutral point. That is the Y-connected current transformer. So how about for this voltage transformers here, is measuring the three-phase voltage in terms of connections. It is also in Y connections as well. So connect in parallel connections to the voltage source. So here, the first terminals here will connect to each phase. This is the first set, the second set, and the third set of current transformer. So another terminals here will actually connect to the ground. So that's how we have the voltage transformer in Y connections. All right, so let's move on here to the next page here. All right, so let's get a better idea why we want to have the instrumental transformer in the electrical power system, or what is its purpose. All right, so for your information, all the electrical measurements and relaying decisions are actually derived from voltage or the current signal. So for this current transformers and voltage transformers, we know that it acts like a sensor through the protective relay. So it's responsible to measure the voltage and current value continuously of a specific part of the power system. So basically, it will give the feedback signal to the protective relays. That's how does a relay recognize that it's a fault occurs within the power system that wants to detect the abnormal conditions based on the settings value. So we know that for relaying hardware, right, is actually work for much smaller range in terms of currents and voltage. So it's impossible to have the monitoring relay here to be being designed for every system components, like let's say for every distribution system here, by having the matching voltage or current value being used. So for example, the current from the feeders and the current from the transmission line, the current value might be different, all right? So we doesn't need to have a relay to being purposely designed to work for the specific numbers of the voltage value. All right, so how actually we can solve these problems here is by using the current transformers and voltage transformer, which are the instrumental transformers here. With such a case, it can allow us to have same types of relays being used for all types of distribution systems. Right, so for this current transformer, voltage transformers here is actually carrying the same working principles as the gyro transformer, the one that we use to step up or step down the voltage value, remember, in order to achieve efficiency of long distance of power transmissions. The one that near to the junction plant, we will actually stepping up its voltage value. The one that near to the users here will step down the voltage value instead. So for this instrumental transformers here, it will carry the same working principle, just that there are the step down current transformer and step down voltage transformer. Okay, so now let's move on here to the next slide. So what we can say, the main task of having both current transformers and voltage transformer that are actually like a sensor for the protective relays, remember? So basically it's responsible to measure or provide the currents and voltage measurements by stepping down the high values of voltage or current from the power line here to a much lower value, which is the acceptable level, which can be handled by the protective relay. So that is the first task, all right, of the instrumental transformer. And at the same time, right, it's also allowed us to have the isolations electrically. So we know that for a transformer is being configured with both primary winding and the secondary winding, right? So a secondary winding will actually connect to much lower rating device. For example, the relay, the metering like the ammeter, 1 meter, watt meters here, as well as any instruments from the actual power system. We know that the actual power systems here will be connected with the primary circuit, which is expecting to having much higher voltage value. So we know that for this low rating device, it's unable to take such high voltage value. So by using this instrumental transformer, it's able to isolate them electrically. So that is the second functions of having instrumental transformers. And one more function here, if we are using the instrumental transformer, it's also allowed us to have the possibilities of standardizing the components like the relays and the instruments here, with its secondary windings here being rated at much lower value, which is in terms of current transfer, it will be rated to a field rated current, which is much smaller. For voltage, also much lower value as well. Okay, so that is basically why we want to apply instrumental transfer as a protective device in a power system. And moving on to in practice, the secondary winding, or I should say the ratings of the secondary winding of the instrumental transfer has been standardized to certain value, or let's say to 5 amp or to 1 amp, depending on where you stay. So with such a case, it's allowed the degrees of interchangeabilities of different manufacturers for the components that the relay or meter to be used within the same power system. So for example, if you are staying in the regions like Asia or Europe like us, right, the secondary windings of the current transfer will be rated at 1 amp. Or let's say you stay at North America, so the secondary current value will be chosen at 5 amp instead as a standard value. Whereby for voltage transformer, of course, its secondary winding will be being stepped down to much smaller value, rated at 110 watt instead. All right, so you can see its secondary values here doesn't change under normal condition, either to 1 amp or to 5 amp, or for voltage should be 110 watts. So it's allowed. We can use the component from different manufacturers together. Okay, so now let's see here. We want to understand the voltage transfer in much more detail. So let's dive into this slide here. So as being mentioned in the earlier class, we have two types of voltage transfer can be used for the protected equipment. All right, so for examples here, the first one we have is known as electromagnetic types of voltage transfer. In short, we will refer it as VT as the short form. So for this VT, the electromagnetic types of voltage transfer is usually used for much lower voltage application. So we use it for metering purpose to get the accurate measurements of voltage for lower voltage systems. How about for another one, we have known as what we call as capacitor types voltage transfer. So in short, we will refer it as CVT instead. So for this capacitor types of voltage transfer is actually carrying the same purpose. Of course, we want to get the voltage measurements, but it's being applied for much higher voltage applications. So for instance, it's generally used for transmissions line for the voltage measurements, which is expected to operate with the voltage rail, which is higher than 66 kilowatt. Right, so that is the difference between these two in terms of applications. So how about in terms of construction? So let's move to the next slide here. We'll focus on the electromagnetic types of voltage transfer first. All right, so if you look into these figures, right, you will see that for these electromagnetic types of voltage transfer, it will consist of the iron core, and there will be a winding here that wound around this iron core here in such a way. The primary winding will give us the high voltage value, in short is HV, and the secondary winding here will give us the low voltage value. So you know this is step down voltage transformer. So take note that for the numbers of winding turns at both sides, right, is directly proportional to the voltage value, or I should say the open circuit voltage value, which is being measured across it. So we know that this is a step down voltage transformer, so we can tell that to get high voltage value at the primary side, so the primary winding turn will be much more higher as comparing to the secondary winding. So you can see it have much lower numbers of turns, giving us the low voltage value. So based on this fact here, higher number, higher voltage. So high voltage at the primary side, low voltage at the secondary side. That's how we construct the step down transformer. Okay, so typically you will see, right, so for these kinds of voltage transfer, it will apply the circuit like this. All right, so this is the primary winding, this is the secondary winding. So let's say I want to get the voltage measurement from this power system. The primary winding will connect with high voltage line in parallel connections, whereby for the secondary winding, which is with lesser numbers of turns here, will connect with low rating device. That's how we have the isolations for the low rating device with high voltage system here electrically. So typically for these types of voltage transfer is being used for the circuit or the applications up to 110 or 132 kilowatts. All right. So right now you can see the primary winding is subjected to system voltage. The secondary winding here is connect with a low rating device like the wattmeter, ammeters, or not wattmeter, or the protective relay is actually placed here at the secondary side. So what happens if, let's say, we have much higher voltage applications? So for these types of voltage transfer is no longer suitable anymore. So we use another kinds of voltage transformer, which is CVT, the capacitor type voltage transformer. The reason why is because it's much more cheaper in terms of cost implementations. So let's check out the constructions of how does a capacitor types voltage transfer is being made. So if you look into these figures, right, you will notice that for capacitor types of voltage transformer is actually make use of the capacitance potentials dividers rule. So you check out here, this is the primary winding. This is the secondary winding. The primary winding will connect with a numbers of capacitors that connect in series. All right, and then the secondary winding here will connect with another iron transformers here. So in such a case, right, we'll notice that whenever we use numbers of capacitors in series, we are actually able to split this high voltage value to much smaller value or to any convenience value. And after this, with this transformers winding here, is further reduced down the voltage value at the secondary side based on the ratios here. What is the VP or VS ratio? Okay. So now because of this design, we have a numbers of capacitors is being used at the primary side. So it's possible to have one common primary winding with two or more secondary winding within the same unit. So you can place another secondary winding here to or another one pair with the first capacitors here. That's how we have two or more secondary windings within the one units of the capacitor types voltage transformers. Okay, so now let's move on here to the next slide. So in terms of working principles, if we are talking for the electromagnetic types of voltage transformer, it will be same as the power transfer that we use to change the voltage whenever we are converting or transmitting the electricity from one circuit to another circuit. Perhaps the only difference, right, seeing as instrumental transfer is working for much lower voltage value. So the difference will be in terms of cooling aspect, the insulation, as well as the mechanical aspect. They are not the same as comparing to our high voltage systems. Right, so seeing as this is used as a step-down voltage transformers, we know that the primary winding transfer will have large numbers of turns, giving us a high voltage value. And in terms of connections, all right, with the power system, it will be across, which means that in parallel connections or across with the voltage source here to either how you want to measure. So if let's say you want to measure the line to line or phase voltage, there is a different configuration for this. So for example, if I want to measure the line to line voltage, so let's say this is a 3 live wire coming from the generators here. So in the event, if I want to measure the line to line voltage or the phase to phase voltage, the primary terminals here will connect with two of the phase, and the secondary winding here will be connect with the low rating device. So with these connections, right, I'm actually measuring the line to line voltage. So how about if I want to measure the phase voltage instead? So in terms of connection, of course, in parallel as well. So for the primary winding, one side will be connected to one of the phase of the winding, and another side I will actually connect with the ground. So with these connections, right, is actually measuring the phase voltage value instead. So comparing in terms of magnitudes, this is the line voltage 415 volt. This is actually the phase voltage where I have line voltage here divided with square of 3. So for these two is for single phase voltage measurements. So for three-phase voltage measurements, I can actually connect the voltage transformers here either in Y connections or delta connection as what we have seen for the overview diagram of the electrical power system in the earlier class. Remember this one here? So if I activate my pointer, so you can see this is actually in Y connections, measuring in for the three-phase system. You can actually change it in data connections as well, depending on the applications. So going back here, right? So we know that this is actually the step-down transformer. For its secondary winding in terms of cost, it will construct with lesser numbers of turns. That's how we have low voltage at the secondary side. But it will fulfill the principles of the transformer, where the voltage per turns at both sides, I mean for the primary side and the secondary side, will actually remain the same as the ideal transformer. All right, so that is for the voltage transformer. So let's move on here. So how about for capacitor types voltage transformer? So if you take into account of cost aspect, the money, all right, so the implementations cost, the capacitor types voltage transformer will be generally used for extra high voltage system because it's more economic viable. So we can use this CVT here for both protection purpose as well as the communication purpose, right? Seeing as the insulating transformer is very expensive. So for this CVT, right, it's actually allow the injections of high frequency signal into the power line conductors. So usually the communication signal is high frequency. So whenever we allow this high frequency inject to the power line, which means that it gives us the purpose of communication. So we are able to have the end-to-end communications between the substations. Let's say we're using a distance relay, all right? So distance relay usually will be applied for the long distance of power transmissions protections purpose here. Seeing as it has long distance between these two lines here, in order to have a quick response to clear the fault for those faults that occurs at the end or at the beginning of the line, we need to have communications from both sides. All right, we can actually have this CVT here to be used to measure what would be the situations of this power line. All right, and at the same time, due to the injections of this high frequency signal, it allows us to use it for voice communications as well. Okay, that is the functions of the CVT. Okay, so let's move on here to the next slide. So for voltage transfer being used in the electrical power system, it should have high accuracy in terms of voltage measurement. So it gives us the less errors. So now we need to learn how to choose the right voltage transformer based on the accuracy class for different applications, like for metering, or is it for protection purpose? All right, so for voltage transfer itself, like it has been classified in according to accuracy class and the burdens rating. So for PT is the potential transfer. It is the another name for voltage. So PT, right, is actually having 3 different accuracy class, and these 3 accuracy class is actually defined by IEC standard. So it's actually telling you what is the guaranteed voltage value being measured at the secondary side within the specified percentage from the rated voltage value from the primary side. So let's check out here, like for instance, if I have the accuracy class of 1.2, this indicates that I can get the correct measurements from the secondary side in between this range, which is 98.8 to 101.2% of its rated primary voltage value. So the next one we have this, let's say I'm choose the one with 0.6. So you can see the accuracy we actually given us from 99.4 up to 100.6% here. And the last one, 0.3, given us the accuracy percentage from 99.7 up to 100.3%. So that is what we have as the accuracy class. So how about for burdens rating? So this is also the standard coming from IEC as well. And we are using alphabet to define the burdens rating. So what is actually the burden is? So if you refer to this dialog box here, so burden is actually known as the maximum resistance that can be connected at the secondary sides of the voltage transformer, in which this burden can actually affect the reading from the voltage transformer. So there is a maximum burden value can be placed at its secondary side. So for example, the secondary side of the voltage transformer can be connected to different devices. For example, like the relay or like the voltmeters, right? These components have the resistance value where we call it as the burdens. And we have to keep these burdens here lower than the burdens rating we can obtain from the specifications of the voltage transformer. So for example, W here, right? So if we are choosing the voltage transformers with W, which means that we have to maintain the burdens below 12.5 watt ampere. So what ampere say is the apparent power, is a unit for the burdens, all right? So if you're able to keep the secondary side with the burdens lesser than 12.5 watt ampere, we are able to get the accurate measurements of voltage. So the next one in line here, let's say we choose the one with X as the burdens rating. So it can give us the accurate transformations of the voltage. Let's say the burdens has keep lower than 25 watt ampere. Okay, the next one Y here is with much higher burdens, but it's below 75 watt ampere. You can get the right voltage measurement. Z here, the voltage, the burdens rating is even higher right now. You have to keep below 200 watt ampere. And double Z here is the highest burden rating you can choose, which you have to keep below 400 watt ampere instead. So this is actually considered as a loss for the voltage transformer. If let's say we have the burdens creating the loss higher than this, it will give you the wrong voltage measurement. So that's how we choose the voltage transformer based on the burdens rating it can take. So let's see how actually we can identify or read the accuracy class as well as the burdens rating for a voltage transformer. So suppose right now you are being given a voltage transformer and its spec is being labeled as such with IEC standard code here at 0.6 ZZ. Alright, so from this IEC standard code, we can understand 0.6, right, which is the second range here, where we are able to tell that if in the event I can keep the burden lower than 400 watt ampere, basically I can get the voltage measurements within this range in terms of accuracy, which is 99.4 up to 100.6%. So that's how we can read these codes here if let's say you want to buy a voltage transformer. Okay, so now this is everything about the voltage transformer. Now let's move into the another big topics here, which is the current transfer. So I can tell you, right, most of the contents we have in this chapter 3 here is actually relates to current transformer. So let's drill into much more details by looking into this slide and onwards. So in terms of constructions for the current transformer is actually similar as the standard transformer we have, but it consists of the magnetic core being coupled with both primary and secondary windings. Okay, so in terms of connections for the primary windings of the current transformer, you have to treat like an ammeters right now, where it must be in series with the power line, which is different as comparing to voltage. Remember, voltage is connect across in parallel connections, but for current transfer, its primary winding has to be connect in series instead. So seeing as it's being connected in series with the power networks, which means that this current transfer for its primary winding must be strong enough to withstand the maximum current flow through the power system. So even under fault conditions. So with such a case, usually the primary winding turns of the current transfer will be constructed with much thicker size of wire so that it's able to withstand the highest current flow, even the short circuit currents. Okay, so as being introduced in the earlier class, we know there are two types of current transfer, and we classify it based on how does the primary winding is being configured. So we have wound primary types and bar primary types of current transformer. So let's check out the difference by looking into some photos here. So this is how it looks like, and this is the cross sections view of the current transfer. So we have wound primary types at the left hand side here. So you can see it consists of the annular core with both primary and secondary winding wound around it. So as being informed just now, right, we know that for a primary side will be connect with the high currents line. So usually the primary winding will be made of the thicker size of wire with big cross sections area so that it can withstand the high primary current flow, seeing as is connect in series with the power line. If we compare the secondary winding with the primary winding, you will notice that the secondary winding here, the size of the wire is actually much thinner as compared to the primary winding because it has been stepped down, so it will deal with much smaller currents magnitudes. So this is for the wound primary types of current transformer. So how about for bar primary types of current transfer? So it's the figures that locates at the right hand side. So you see, right, if you notice here, yes, it consists of the iron core, but it only has the secondary winding wound around it. So the primary winding would be the power line itself or the bus bar itself. So you can treat this one is like one single turn for this bar primary types of current transformer. Okay. So usually for this primary is being designed being fully insulated from a high operating voltage. So in terms of applications, for wound primary types of current transfer is generally used for smaller currents measurements. So you can see it's applied for lower voltage applications, seeing as it had low fault level thermal limitations. So for those current that's higher, let's say more than 100 amp, we will use bar primary type instead for the measurements of the current. Okay, so now let's move on to the next slide here. So focus on the bar primary types current transformer. So now if you check out this image, right, the highest point is actually what we have as a high voltage terminal. So you can consider this one is like the primary circuit. And then here at the center, we have what known as a gas cushion. This gas cushion is actually a thermal seals expansion system that is used to compensate the volume change due to the temperature variation. So typically inside will fills with nitrogen gas. And at the bottoms here, the one I think is in red colors, we call it as the porcelain insulators. So inside this porcelain insulator, right, it has a magnetic core for the instrument, for current transfer that have been wound by both primary winding and the secondary winding. So for this magnetic core is being used to generate the magnetic flux, we know, for the transfer operations so that the power can transfer from the primary circuit to the secondary circuit. So take note that for this porcelain insulator is also work as the isolator. So it will insulate the winding, both primary and secondary winding here from the earth outside. And lastly, at the bottoms here, we have secondary terminal spots. So depending on what is the applications, so the terminals here can be connected to ammeters. Let's say you use for metering purpose to get the current measurements only, or you can use for protection purpose. So here you will be able to connect to protective relays. So that is what we have for the bar primary types current transformer. All right, so based on the exterior design of the applied device, all right, we can actually use the current transfer for the current measurements. So for the current transfer core as well as its secondary winding can actually directly install at the pushing of the circuit breakers as well as the transformer. So remember, this is the lifetime design of the circuit breakers. That's what we have learned last week. So we call these kinds of current transfer with these connections as the pushing current transformer. So pushing current transfer is always chosen for a relay in much higher voltage circuit because it's less expensive. So let's check out this image here. So we have bar primary types current transfer. How I know this? Because I have iron core only wound by the secondary winding. And this iron core has been arranged in a way to encircle, right, this insulated bushing, or I should say this is the power line, which is carrying the primary current. So this primary current will step down to much lower currents required as the secondary currents based on the numbers of turns here that's wound around the core. So how actually I can find the currents here is based on these equations here. So the step down current at the secondary side can be found by having the primary currents divided with the turns at the secondary side in terms of winding turns. So this is the ideal condition. That's how we can find the step down current. So for information, there's a total load able to connect at the secondary side of the current transfer. So we know that this is the secondary winding turns here. So we could have different components to be connected here to get the current measurements. So for terminal G and H here would be what we have as the secondary terminals of the current transformer. So for whatever components, for this case here, the relay is considered as the burden for this current transformer. So in order to get the right current values measurements, this burden should keep as small as possible following the burdens rating as what we have learned for the voltage transformer. Okay, so now let's move on here. So this would be the circuit symbol for the current transformer. So this is a power line. This is the current transformer. So usually we see this in the single line diagram. And there's one important parameters for the current transformer, which would be the CTR, the current transfer ratio. So let's check out what would be its definition. So for current transfer ratio is being defined as a fraction, which means that we have divisions. The ratio between the magnitudes of the primary currents to the secondary current for the ideal working conditions for the current transfer. So mathematically it's being calculated as such. Where CTR, how much current has been transformed down, we can calculate based on the primary current's magnitude divided with the secondary current's magnitude. Or alternatively, we have another equations here. We could have the ratios of circuit current to the relay current. So how actually I can get these formulas here to find the CTR? So let me draw attention by looking into these figures at the right hand side. All right, suppose this is a power line and I want to apply the current transfer to measure the current. Right, so let's say this is the current transformers. Okay, and the primary side I have the circuit current flow we create as the primary current. So we know that for this current transformers, right, is not transmitting the actual current value to the low rating device. Like let's say I apply to the overcurrent relay. I need to step it down based on the current transfer ratio, correct? So with such a case, the secondary current, which is the step down current, will actually fit to the relay. So these secondary currents can also known as the relay current flow. So with such a case, we can also find the current transfer ratio by having the circuit current divided with the relay current. Okay, that's how I can get the models here. Okay, so from here, right, we know that the primary current is always bigger than the secondary current. So the denominator, we know is the secondary currents either rated at 1 amp and 5 amp. And these numerators here, which is at the top here, is always higher than this. Yes, it can be the rated current flow at the primary side. That is only under normal conditions for this power system. But this circuit current here could be the fault current as well. So usually these top parts here, the numerators, it not necessarily the rated current flow, it could be the short circuit current. But the secondary currents here always standardized to a certain value, either 1 amp or 5 amp, depending on where you stay again, or depending on the applications. Okay, so let's check out some examples here. So now we have different conditions of different current transformer. So suppose if you have the normal current flowing through the power line here is 200 amp. And we know that the secondary current has been standardized to 5 amp and then sent to the overcurrent rate, for example. So if we want to find the current transfer ratio, will be 200 divided by 5, which is 40. We know this is the CTR value. Or reversely, if let's say the question give you in terms of CTR, and we know that the normal current passing through the primary coil here is actually 1200. We can also find what is the secondary current value as well, all right, by having this 240 divided with 1200. So we get the value. We know that the secondary current has been standardized to 5 amp. And one more last example here. What if we have the calculated current transfer ratio at 400, and we know that the secondary current has been standardized at 1 amp? We can also interpret that this primary current is actually 400 times bigger as comparing to the secondary current. So that's how we decode this current transfer, by looking into the current transfer ratio. Okay, so now let's move on here. So let's talk about the wound primary types current transfer in much more details. So in terms of application, just now I have been mentioned, is being used for smaller current measurements. The reason why is because on its thermal limitation in terms of construction, it's only able to provide low fault levels of protections. So how about for the current which is more than 100 amps? So for any higher ratings current power networks, we will actually use bar primary types instead. Okay, so what happens? We know that we have a secondary winding wound around the core for this bar types current transfer. So if the secondary winding has been distributed evenly around the core like this, so instead of focus at one sections of the core, it's being wound around like this in distributes evenly manner. So under these situations, the leakage of the flux can be eliminated. So with such a case, we can also say the leakage reactance can be ignored. So it will not flow through and leak through the air gap. So that is basically why we have evenly distributed of the secondary winding instead, so that we have a much better performance for the current transformer. Okay, so now we have learned about the current transformer and voltage transformers, right? So let's check out these tables here to see what are the difference. So in terms of functionalities in the power system, this is quite obvious from the names you can tell. Current transfer, what is doing here is actually trying to help you to transform the high current value from the power line to much lower value, so that it can be conveniently measured by the load reading device. That is the functions of the current transformer. Then for voltage transfer, yes, you know what is it doing? Transforming the high voltage value much to lower voltage value here. So you know this is a step down voltage transformer. Okay, so how about in terms of connections for a primary winding with the transmission line? So in the event, if I want to measure the current value from the transmission line, so for the current transfer as being mentioned, you have to treat it like an ammeter. So it has to be connected in series with the power line. In this case, here is the transmission line. So again, whenever we have series connections with the transmission line, the constructions of this primary winding must be strong enough to withstand the maximum current capacity from the power line even under fault conditions. How about for voltage transfer? It's like a wattmeter. It has to be connected in parallel connections with the transmission line, measuring either face-to-face or the line-to-line voltage. So how about for the core structure? So we know that for a transformer is being mixed with core, right? So for current transformer, right, it's actually mix of laminations of the standard steel. So which means that we have a multiple piece of steels being stacked together and compressed from the laminations. So the intentions of why we're not using a big steel instead of the laminated stainless steels here is because we want to reduce the eddy current loss, right, or reduce the hysteresis loss. So that is the constructions in terms of core for the current transformer. So how about for voltage transformer? It will be built with the high operating core that are operating at low flux densities, all right, so that we can prevent this core of the voltage transformers here turn into saturations. So that is in terms of core structures. How about in terms of numbers of winding turns at the primary side? So for current transformer, you will notice that the primary winding has lesser numbers of turns. So how I know this, all right? So now we know that for transformer, for current transformer, it will actually fulfill the principles of any standard transformers, right? So it will satisfy the ampere turns ratio, whereby both side, primary side and secondary side will be the same. So for either transformer, we have such a formula, all right, where the ratios of the primary turns to the secondary turns will be equivalent to the secondary currents divided with the primary current. So let's rearrange this in terms of secondary current. So you'll find that secondary is the primary current multiplied with the numbers of turns at the primary side divided with the secondary numbers turns, right? So we know that this is step down current transformer, so which means the secondary currents will be reduced. So with such a case, if you check out the relationship in terms of winding turns at the primary side, that are directly proportional to each other. So we know that the secondary current has to be stepped down, so the primary number of turns has to be reduced. So that's how I know that the primary winding turns for the current transformer is actually much lesser as comparing to the secondary number turn. But how about for voltage transformer? Remember, we have seen this relationship where the magnitude of the voltage generated at the voltage transformer is directly proportional to the numbers of turns. So we know that this is step down transformer, so the primary side will have much higher voltage value. So in terms of primary numbers turns, it will be much more bigger as comparing to the secondary side. All right. So that is in terms of numbers of turns. And how about for the impedance comparisons between the primary side and secondary side? So this is actually interlinked to each others. So we know that the winding turns is actually configured with wire, right? The higher numbers of turns, which means that you are using a longer wire will give you a higher impedance. So from here, we know that the secondary side will have much higher winding turns. So we know that for current transformer, the secondary winding impedance will be much more bigger as comparing to the primary side. So how about for voltage transformer? You know, primary side is higher number turns, so primary winding impedance in this case is higher instead. So the last one to be compared between current transformer and voltage transformer will be what is the precautions you have to take note on whenever we are using this instrumental transformer for measurements. So in terms of connections of the secondary side for the current transformer, right? Let's say you want to use it for current measurements. You cannot left the secondary side open circuit, all right? But then for voltage, no issue. You can actually have it to be open circuit even though you use it for voltage measurements. So what is the reasons that we can't have this current transfer is secondary side to become open circuit? Right? You can actually find the answer in the next slide here. All right, why secondary side of current transfer cannot be left open circuit? So we know that for current transformer and the ammeter that always used together for metering purpose, let's say you want to use it for current measurements. So for current transfer, let's say we have this as a core, and this is the bar primary types current transfer. This core has been wound by the secondary winding. So this is the power line that we want to get the current measurements. And the secondary windings of the current transfer will be connected to the ammeters for measurements purpose. So for these ammeters, right, usually have a very low resistance value. Okay, so with such low resistance value, the voltage drop across the secondary winding will be very small, which is approximate only 1 volt if we have a full primary current flow or the rated current flowing through the primary side. So this is under normal conditions. So we want to get the current measurements. So both primary winding, I should say the primary side and the secondary side here will actually produce what we call as the MMF, the magnetic motive force here, which is actually opposing to each other if, let's say, in according to Lenz's law, right? That is the normal operations for a transformer. So what happens if this ammeter is removed? So I want to do the calibration. I remove this ammeter. So it will form an open circuit at the secondary side. So with these situations, right, remove the ammeter, the secondary winding become open circuit. This current transformer will turn into a step-up voltage transformer, which could generate a very high voltage value at the secondary side. So with such a case, whenever you open it up here, so there will be no opposing force from the secondary winding. So this in turn will result a high magnetic flux being dragged within the core that could cause this core here turn into saturations. Right? So whenever we have high flux being dragged, which means that it will also induce a high voltage at the secondary side. That's how it's turned into the step-up transformer. So what happens if we have high voltage here? So high voltage will cause the damage to the insulation, so it has a tendency that causing the electrical shock to the users. So which means that if we have the energized current transfer, which means if you make use it for the current measurements, you can't left the secondary side of the current transfer become open circuit. So usually we will have a small burden loop here being connected at the secondary side. Okay, so to further explain this, let's look into the simplified circuit for a current transformer. So now this is actually the current transformer, the primary winding, the secondary winding. So the primary winding will be connected in series with the power line. The secondary winding here will connect with low rating device. For example, this is an ammeter with the impedance of Z in terms of load. Right? Usually this Z value here is very small. So whenever we have the load connect at the secondary side, we will have secondary current flow. So due to the core axis for the current transformer, the primary current flowing through the primary circuit, the flux will actually generate. So with such a case, the power will generate at the secondary circuit. And how to measure the power here would be I square R, or I have the secondary current square. So how about the voltage drop at the secondary winding? It can be calculated based on Ohm's law, just the current multiplied with the impedance. That is the induced voltage at the secondary side. So from these two equations, right, we can actually deduce that whenever the load here, the Z value reduce, right, if this Z value reduce, the power becomes smaller, okay? Whenever we have a constant primary current flowing through the secondary terminal. So what happens if I short circuit the secondary side? So whenever I have short circuit the secondary side, the Z is actually equal to 0, short circuit conditions. So if we put Z is equal to 0, I can also say that the power flow at the secondary side is actually 0. And the voltage induced at the secondary side here 0 is also 0 as well. So no voltage being induced at the secondary side. So with these calculations, right, I can tell you that the secondary side of the current transformer, yes, you can keep it short circuit without any risk. But what happens if I have it open circuit. So we go to the next slide here. So in the event if the secondary side here have open circuit, which means that this Z is approaching to infinity. So theoretically, if you look into this power and voltage equations, right, these two value, the power and induced voltage, should be infinite, all right, if I have open circuit conditions. But this power and voltage value will be limited by the magnetic and the copper loss, okay? So let's check out what happens if I have secondary side become open circuit and the Z value, the loads here is approaching to infinities. You will notice that if this value is high, in terms of voltage and power is high as well. So the secondary voltage can reach to very, very high value, which could be reached up to several of kilowatts, creating over voltage conditions at the secondary terminals here. That's how it turned into the step-up voltage transformer instead. So with such arrangements, if you open circuits here, it can actually create the dangerous situations for both equipment itself, which is the current transfer personnel. So what we can say, the secondary side of the current transformer should not left open circuit, right? That is basically one of the issue phase where we need to deal with if we are using current transfer for measurements. So what we can do in the event if I want to disconnect this ammeter for calibrations. So the answer you can find here. So the answer would be like this. So it's fine for us to terminate the secondary terminals of the current transformers with small resistor, or you can apply a switch here so that you can use it to disconnect the ammeters or connect the ammeters. So for example, if you check out the figures at the bottoms here. So let's say this is a current transfer, this is the primary winding, this is the secondary winding. Secondary winding connects with the ammeter so that how we can get the measurements. So you will notice that the secondary terminals of the current transfer has been connected with the switch. Okay, so in the event if I want to remove this ammeter, I just on this switch, form a short circuit connection. So remember, short circuit here, no issue, right? No voltage generate, no power flow. So we can actually short it without any problems. So after you have done the calibrations, then you connect it back and open up this switch for current measurements. So that's how we deal with these problems. Okay. So for current transfer itself, there's different ways for us to classify whether we have what kinds of current transfers right now based on its functionality. Okay, we can actually use current transformer for measurements, of course, as well as protections. So there are actually different properties should have for a current transformer that used for measurements purpose being listed down here. So in terms of burdens rating, which is the connected device at its secondary side, if we are having a measurement kinds of current transfer, it has much lower tolerance as comparing to the protection class of current transfer, which means that the total numbers of loops you can connect at the secondary side is actually much lesser as comparing to the protection class of current transformer. Measurements current transfer, it should give us the high accuracy within this range, which is 5 to 125% of the rated current flow or normal current flow. All right, same as we are used for measurements only, is not used for protections. So for this current transfer, is not expected to give us the linear response whenever we have high fault currents, which means that this current transfer, if we have fault current flow, it might actually give us the wrong measurements. But seeing as this is only deals with lower current flow, so it doesn't expect us to have a linear response in such a case. So it doesn't need to deal with the large current value. So how about for protection class of current transformer? So this device, right, the secondary side will be connect with the relay instead. So this one will be connect with ammeter. So if we are using the current transfer for protection purpose, it must be able to give us the linear response instead, which is up to 20 times of the rated current flow. So which means that let's say 100 amp is our normal current flow. So if we have fault occurs causing it up to 20 times higher as comparing to the normal current flow, this current transfer is still able to give you the measurements for the current. That what does it mean? But for measurement class, it doesn't have these requirements. So with such a case, we can say that for protection class of current transformer, it should give us the correct measurements within the range from normal up to fault current values. And in order to do this, let's say under fault situation, it's still able to give you the right current measurements. The secondary side, the burdens value have to be kept as low as possible so that we are able to get the linear response. So whenever you see linear response, which means it gives you the correct current measurements at its secondary side. Okay, so now there might be time where we will use the current transfer for both purpose, which means that other than used for protections, you can also use for measurements as well. So this indicates that whenever we have such requirements, the current transfer should give us the accurate reading from a very small value up to very large values, which is under fault conditions. However, it is not reasonable to assume that we could have the linear response, which is independent with the total burdens being connected at the secondary side. Remember, how many components being placed at the secondary side will actually affect its measurements value. So usually for a current transfer, it will be given the spec like this, where its nameplate will specify what would be the voltage limit can be generated at its secondary side. For example, 100 watt would be the knee point voltage value, where if you're able to keep the secondary side with the voltage lower than 100 watt, then the linear response will be expected. So what happens if you connect the burdens here, causing the voltage drop across it higher than 100 watt, which means that it's exceed the limit in terms of burdens. It will have the saturations of current transfer intense if we give you the wrong reading. So if we use for protections, which means that now the relay is getting the wrong measurements from the current transfer, so it might misjudge the system. So that's basically how we find the specs of the current transfer. It will be being specified in terms of the point voltage. Later we'll see this in much more details. So I think it's 1 hour marks right now. I will give you like 5 minutes break. Then I will proceed the topics we have here in terms of magnetizations curve. Any questions before I give you the break? Hello? So I see no response, so no questions. So let's take 5 minutes break so we come back the class here at 4:08 p.m. or 4:10. Okay, so let's break.